this lecture, we're going to study one of the simplest methods, the explicit Euler method, to solve initial value problems. So usually initial value problem is given by the equation, the rate of change of a function. For here, in this example, we call it, the function is x. The rate of change of x with respect to t is given by a particular expression, a particular function of x and t. If I know the value of x, the function x that I'm trying to find, if I know a particular value, let's call it xi, at a particular value of time, let's call it ti, as we mentioned previously, usually initial value problems are related to or described by rates of functions with respect to time. So it's okay for us to assume that t represents time. So if I know xi at a particular value of time ti, then we can use a Taylor approximation to estimate the value of x at the next time point, which is at time is equal to ti plus 1, which is the value of x at ti plus 1. We can use this expression. X at the time point ti plus 1 is equal to x at the time point ti plus the rate of change of x multiplied by delta t, and delta t here we're using h to represent it. H is equal to the difference between ti plus 1 and ti. This Taylor expansion has an error term that's directly proportional to h squared. I already know an expression for dx by dt, and dx by dt we're evaluating it at time ti. Dx by dt is given by the expression f, so I can evaluate f at xi and ti, multiply by h, and this expression is equal to this expression. If I ignore the error term, then I can assume that the value of x at time ti plus 1, namely x I plus 1, is equal to x sub I plus the expression f evaluated at xi and ti multiplied by delta t, and delta t here is given by h. And the error term, as we mentioned earlier, is directly proportional to h squared. And this we call it local because that's the error associated with one time step. If I'd like to do this on a large interval of time that's divided into n number of steps, such that or these number of steps are equal to the length of the interval divided by h, then the error is equal to the total error is equal to this error term that's directly proportional to h squared multiplied by L divided by h, which means that the error term is directly proportional to h. Let's try to visually look at what we're trying to do. We're trying to find the function x as a function of time. All I know is the rate, dx by dt. What we're saying is that xi plus 1, or x at the time ti plus 1, is equal to xi plus this function f multiplied by delta t. What we know is the rate, dx by dt, evaluated at x is equal to xi and time is equal to ti, which is evaluated using this expression. Knowing this rate, I can just use it to approximate the function, and after a period of time h, which is equal to ti plus 1 minus t sub I, I can find the value of xi plus 1 using that slope, and you can see the difference between xi plus 1 and the true value is given by ei plus 1, which is the error evaluated with this step in time. Here we've given you some code that, given an expression for the dx by dt, we call it here fb, and given the initial value of x at an initial value of time, so given a particular value for t0 and a particular value for x0, and given a particular step in time, so given h, and given the maximum time, this code will give a table of the values of x of the time and x and x as it moves forward in time. Let's let's go through an example to see how this method works. So let's assume that the Canadian population at time equals 0, which is, let's say, the current year, is given by 35 million. And so right here we know t0 and x0. x0, which is, let's assume x0 is the population. T0 is 0. So at t0 is equal to 0, I know x0 as 35 million. So if we assume that 2.5% of the population have a child in a given year, which means that the number of children born, or the addition in the population, is 2.5 over 100 multiplied by the population. And let's assume that the death rate is 1% of the population. So the population loses 1 over 100 multiplied by the actual population per year. And what will be the population in 50 years? And so we know the rate, and we want to know how this population will change over the years. So notice we started with a birth rate of 2.5%. So this will be case 1 that we are going to attempt. Another case is, what if the birth rate is 6%? So we're going to increase the rate and see how this affects the error of the method. And we're going to keep, in the second case, we're going to keep the death rate constant. Again, we'd like to know what the population will be in 50 years. All right. So the rate of growth will be equal to the 2.5%, which is the birth rate, minus the 1%, which is the death rate. And so the rate of increase is the 0.015. And so the rate of change, dx by dt, how much the population increases per year, will be equal to 1.5%, which is 0.015 multiplied by the actual population. Luckily, this expression, we can find an exact solution for the function x. And if we integrate this equation, we'll find that x as a function of t is given by this expression. X is equal to 35 multiplied by e to the power 0.015 t. So we're going to attempt to solve this numerically using the explicit Euler method and compare the numerical solution with this exact solution. So how are we going to do this using the explicit Euler method? By dividing the time period into small time steps. And so we're going to use time step of 1, so 1 year. And we're going to assume at time 0, we know the population as 35 million. Then we're going to use the explicit Euler method to find the population x1 at time equal to 1 year. Then we're going to find the population x2 at time is equal to 2 years, and so on. Since we know x0 as 35, the population at year 1 is equal to the population at year 0 plus delta t multiplied by delta x by dx by dt evaluated at x is equal to x0 and t0. Now, dx by dt is given as 0.015 multiplied by x. And so x0 is 35, h is equal to 1, dx by dt is 0.015 multiplied by x itself, and so we get 0.015 multiplied by 35, which means that the population at x1 is 35.525 million. Repeating, x2 is equal to x1 plus h multiplied by the rate evaluated at the point x1 and t1. Again, x1 is now given as 35.525, which is the population from point x1 plus the rate, which is 0.015 multiplied by 35.525, gives me 36.0579, and so on. Here is a table that shows the value of time, the value of xi, the value of dx by dt, and the value of xi plus 1, which is evaluated as xi plus dx by dt multiplied by h, and h here is the time period or the time interval, and the time interval is given as 1 year. The error after 50 years, if we follow this table, we evaluate the population after 50 years. The population after 50 years is given as 73.68. The error is equal to the true value, which is evaluated by finding the exact solution to the differential equation, which is given by 35 e to the power 0.015 multiplied by 50 minus the numerical value obtained using the explicit Euler method. The difference is 0.4. You can see that the error is actually very, very small, 0.4 million. And the error is actually very small because the slopes that we are using, the rates, which is 0.015, the rate of population increase is actually very small, which makes this method work really well. So don't forget that the relative error here is given is 0.005. Now we're going to see what happens if we use a higher rate of increase in the population. If we use a birth rate of 6%, we'll see how will this error change. Right here in front of you, you'll see the curve that shows, the blue line shows the exact solution of the population versus time. The black dots give me the explicit Euler solution. We intentionally draw it using dots. We don't connect them, just to explain that we obtain the solution by each dot. We used it to find the solution in the next time point, which is the next dot. And I choose here not to connect them with any lines. All right, let's see what happens in case 2. In case 2, I have the rate of increase of the population is given as 0.05. This 0.05 is the 6% of birth rate minus the 1% of the death rate. The exact solution is given by 35 e to the power 0.05t. And you can find the exact solution simply by integrating in Mathematica, and you find online, in your online notes, you'll find the code that helps you to do this type of integration. The numerical solution is given as follows. x1 using explicit Euler is equal to x0 plus h multiplied by dx by dt, and we evaluate dx by dt at the initial point, which is evaluated at x is equal to x0 and t is equal to t0. And so in this case, x0 is 35, h is the 1 year, dx by dt is equal to 0.05 multiplied by x, and in this case we're going to use x at the initial point, which is 35. 35 plus 0.05 multiplied by 35 gives me 36.75. I can use the 36.75 in the next interval. Dx by dt is now given by this value. Xi plus 1 will be equal to 36.75 plus dx by dt multiplied by h, which is 1, will give me this value. And so on. I can fill the table. And finally, I can see the final value at the end is 401 million. When evaluate the error, which is given by the true value minus the numerical value obtained using the explicit Euler method, you are going to find that the difference is 25 million. The relative error here, which is that 25 million divided by the true value, is given by 6%, which is much higher than the error obtained when the slopes were smaller, when the birth rate was smaller. And you can see here, this is the difference between the true solution given by the blue line and the numerical solution given by the black dots. Of course, the accuracy of the solution depends on the chosen h. If you go to the example online, you're going to find a tool and a slider. Once you change the slider, you could see the effect of the value of changing the value of h on the solution. The blue line is the exact solution. The dots is the obtained numerical solution. As I make h smaller, you're going to find that the black dots all are almost overlapping with the blue line. When I make h bigger, which means I make the time step bigger, you're going to find that you lose accuracy, and of course the accuracy decreases. It decreases as we march forward in time. We're going to go now through another example, slightly more complicated example, and I have to acknowledge the page where I borrowed this example from. I put here the link, and you can, if you visit my the web page where this is obtained from, you can find the link that will take you to where I borrowed this example from. So we have a lake that has a volume of 10,000 meter cube and has an initial concentration of a particular pollutant of 5 parts per billion. And this concentration is given as a volume concentration, which is the volume of the pollutant divided by the volume of the fluid. This pollutant is due to a particular pesticide that's no longer available in the market. One assumption that's very important is that the volume of the lake is constant throughout the year. And so if right here in the picture, the lake is represented by this box, by this rectangle. This lake, there's water flowing in and water flowing out. The water that's flowing in, of course, is equal to the water flowing out because the volume is constant, which means water does not accumulate in the lake. It's just whatever goes in also comes out, according to a particular equation that's function of the time. And this depends on the on t, where t is given as per day. Depending on which day in the year, the value of Q is given by this, which is a volume, the volume entering or exiting per day. This pesticide is no longer used, and so in the surrounding environment, the concentration was given, which is given as part per billion, is decreasing according to this equation. The concentration is equal to 5 multiplied, is decaying by this equation, and is equal to 5 multiplied by e to the power negative t 2t over 1000, which of course indicates that the concentration is following an exponential decay. It's decaying, and this is the concentration in the of the pollutant in the surrounding soil. And so as if the water flows from the surrounding soil into the lake, it will go in with the pollutant, will come in with that particular concentration. As given here, this concentration can be assumed to be that of the pollutant in the fluid flowing into the lake. Now, the concentration of the pollutant in the fluid flowing out of the lake, of course, is the same as the concentration in the lake. So if the concentration in the lake is C, the concentration flowing out of the lake, of the fluid flowing out of the lake, is C as well. And so we want to know what is the concentration of this particular pollutant in the lake after 2 years. So obviously, the concentration flowing in is decaying, which implies that the concentration in the lake should be decreasing. It starts at 5 parts per billion. We should expect after 2 years to decrease. And so the hard part in this example is actually to write the differential equation. So how do I write this differential equation? So I'm going to take you through the steps. So I'm going to go here through the steps by which I can build the differential equation that I need to solve to find the concentration after 2 years. And the differential equation should be a rate equation. It's an initial value problem. It should be in the form of dc by dt. How do I find dc by dt? So this is what you see here is just a schematic of the problem. I've got the lake represented by this rectangle. I've got something flowing in, the fluid flowing in with a concentration of C in, and the fluid flowing out with a concentration of C. The rectangle, the size of the rectangle stays the same as because the volume of the lake here, we're assuming it's the same. It does not change over time. And C is the concentration in the lake, and this is what we're trying to find over time. First, let's think of the term concentration. The concentration here is given as part per billion. The concentration is a unitless quantity, so we're assuming that it's equal to the volume of the pollutant, and here I'm using POL to represent pollutant, divided by the volume of fluid, and it's part per billion, so it means it's times 10 power 9. Q, which is given in the problem, is equal to the volume of the fluid that's coming into the lake per day, which is also equal to the volume of the fluid that's going out of the lake per day. And so Q is equal to the volume of fluid that's coming in per day, or the volume of fluid that's leaving per day. The volume of the pollutant that is coming in per day, if you look at what concentration means and what Q means, you'll realize that the volume that's coming in per day will be equal to the concentration that's coming in multiplied by Q divided by 10 power 9. Similarly, the volume of the pollutant that's coming out of per day will be equal to the concentration C multiplied by Q, which is the fluid exiting or leaving the lake, divided by 10 power 9. The concentration of the lake that we're trying to find is actually equal to the volume of the pollutant in the lake divided by the volume of the lake multiplied by 10 power 9. That's just from the expression of the concentration. So C is equal to the volume of the pollutant divided by the volume of the lake times 10 power 9. The rate of change of the concentration is equal to the volume of the lake is constant, 10 power 9 is constant, so what changes the concentration is just how the volume of the pollutant changes. So the volume of the pollution with respect to time will be what makes the C changes with time. Now, of course, how does the volume how does this change? We already know how much volume is entering per day, how much exiting per day. Therefore, dV by dt is equal to the volume of the pollutant that's coming in minus the volume of the pollutant that's going out per day. And so that means that the equation is given by this: dC by dt is equal to Q divided by V lake, or the volume of the lake, multiplied by Cn minus C. Remember, the unknown here in the equation is C. That's what we're trying to find. Q is given in the problem, the volume of the lake is given in the problem, and the C, the concentration of the concentration of the pollutant coming into the lake, is also given in the problem. So C is the function that we're trying to approximate, or trying to find over time. And so this is the expression after we substitute with the volume of the lake, Q and C in. And so what you see here is what we described at the beginning as an initial value problem. dC by dt is given as an expression function of C and of time. This cannot really be solved. There's no explicit solution for this. I won't be able to find an explicit form, or it's not easy to find an explicit form for what the concentration is over time. So can only solve it using a numerical method, which is, we're going to use the explicit Euler method. And so given this expression, now it's very easy to apply the explicit Euler method. In the numerical solution, I know initially when the time is 0, the initial value of C is 5 part per billion. What happens at t equal 1? The concentration at t equal 1, I'm going to call it C1, is equal to the initial C0 plus h, which is delta t, multiplied by dc over dt, evaluated at the initial point, which is c naught and t naught. C naught is 5, h is 1, dc by dt is all this expression. In this expression I have time and I have concentration. Time I substitute at time naught, which is 0. C I substitute with c naught, which is 5. So you put here time is 0, c time is 0, and c is equal to c naught is 5. Evaluate this expression at c, that c1 is equal to 5. So the numerical solution predicts that after 1 day, the concentration does not change. It's still 5. At t equal to, c2 is equal to c1 plus h multiplied by dc over dt, evaluated at c equals c1 and t is equal to t1. So these are evaluated at the previous time point. c1 is given as 5. So wherever I see c1, wherever I see c, I put 5. T is equal to t1. T1 was equal to 1, and so every time I see t, I'm going to put 1. And so at C2, after 2 days, the concentration becomes 4.9999. And so you can see it starts to decrease after 2 days. Okay, so as you continue, you can do this for 2 years. 2 years is however many days, 365 multiplied by 2. You can see that the concentration decreases over the period of 2 years. And you will be able to find that after 2 years, the concentration reaches a particular value less than 2 parts per billion. And you can see that this has kind of it's the overlapping of two functions. The exponential decay that's happening for the concentration that's coming in, and you can also see the periodic change because of due to the periodic nature of the fluid that's going in and leaving the periodic nature of the fluid coming in and leaving the lake. The last example in the explicit Euler method we will it's a very simple example, but just to highlight one of the major disadvantages of the explicit Euler method, mainly the stability of the method. We're not going to cover the theoretical aspects of the stability. We're just going to show an example that describes the possible instabilities associated with the explicit Euler method. So here we're going to give an equation, a simple equation. If the rate dx by dt is given by negative x, the rate of change of a quantity x is equal to negative 1 multiplied by x. We're going to assume that at the initial time point, at t equal t naught, x naught is 1, so we start with the population. Let's say this is a population of some sort. We start that it starts at 1, and it's, of course, it's decreasing because dx by dt is equal to negative the value, which means the x is decreasing over time. And we want to try this with two different time steps. H is equal to 0.1 and h is equal to 3. The exact solution is given. I can find the exact solution. X is equal to e power negative t, so it's an exponential decay. Now let's see what will happen if I use the explicit Euler method. If I use the explicit Euler method, xi plus 1 at time ti plus 1 is equal to x at time I, ti, plus h, which is delta t, multiplied by dx by dt, evaluated at xi. Now dx by dt is equal to negative x, and so I can simply replace dx by dt with negative xi. So I've got xi minus h xi. I will take xi as a common factor. I'll have 1 minus h. Now remember, I can repeat this again for xi. We'll make it equal to 1 minus h multiplied by xi minus 1, and so on, which means that xi plus 1 is equal to 1 minus h to the power of I plus 1 multiplied by x naught. Now let's look at this expression, 1 minus h to the power I plus 1. If h is a small number, such as 0.1, we'll get 0.9 power I plus 1. 0.9 power I plus 1, this value is bounded, which means every time you increase I, this number will just get smaller and smaller. 0.9 power 2, 3, 4. As this number increases, this value will decrease. But now let's try to put a high number. For example, h is 3. So if I put here 3, so this 1 minus 3 will be negative 2. So this number will be negative 2 power I plus 1. Now let's think about what will happen to this number. When I is 0, for example, or I is 1, this will be negative 2 power 2. It's going to be a positive number. When I is 2, this will be negative 2 power 3. This will be a negative number. This number, in fact, will oscillate rapidly or wildly, leading to an instability in the numerical scheme. So let's see visually what will happen. If h is a small number, I will get a very nice solution. The orange line is the true value. The black dots are the numerical values. As h increases, so I'm using a higher h, I'm going to lose accuracy. So I will get the black dots versus the blue line here. As I increase h further, you're going to start seeing these instability in the solution. There's wild oscillations. I started at 1, become negative 0.5, then go up to 0.25, and so on. So you get these oscillations. As I increase h even more, I get wilder oscillations and render the solution the numerical scheme is called unstable in this case. So this concludes the explicit Euler method. In the next lecture, we're going to study different or other methods that are similar to explicit Euler method for solving initial value problems.